Welcome to a code report solution video. In this video, we're going to be covering an alternative solution to a problem in our dynamic programming video series, problem 4, abbreviation, which we covered last week, but this will cover a different dynamic programming approach to solving this problem. So here is the problem statement. I will have a link up here to watch the previous solution, which I recommend you watching if you haven't done already, because it will add color and motivation to this video. But basically the problem statement is that we're going to be given two strings A and B, and we want to translate or convert string A into string B. And the way we can do that is by either removing lowercase letters or converting the lowercase letters to uppercase. So we're given two examples in the problem statement here, A, B, C, D, E, where B and C are lowercase, and then the string B is A, B, D, E. And we can see here that if we capitalize the B and delete the C, we can get A to B. But in the second example here, we have the same string A, but the string B is A, F, D, E, and there's no F here, so we won't be able to. So you either have to output yes or no, depending on whether it's possible. So in the previous video, I showed an example where string A was lowercase a, b, a, a, and then uppercase A, and string B was two capital A's. And the solution involved recursion and memoization. So you can see the recursive calls here. We basically would make one recursive call where we would delete a lowercase letter if possible. And we would make another recursive call where instead of deleting the lowercase letter, we would capitalize it if we could. And you can see here that we've deleted the A, and then we have a new string A at this point, and then we capitalized the A here and then went on from there. And so if at any point we have sort of two uppercase letters that don't match, we can't recurse anymore, and we're trying to get to a state where A is equal to B. And the memoization showed that there was certain states of this recursive tree that overlapped, and therefore using memoization and a couple other optimizations you could solve this problem. However, we're going to cover an alternative solution, which is a more sort of classic dynamic programming, which relies on a recurrence relation, which is actually represented by our two left and right calls here. So we're going to get rid of this. And what we're going to do basically is we're going to create a two-dimensional array that is indexed by the length of our string A and the length of our string B. So we'll call this N and this M and have indices I and J. And then we're going to have this table here. So I is going to loop across our string A, and then J is going to loop across our string B. And these represent sort of the characters at the indices 0 and 1, and the same here. And we're going to initialize our 2D data structure, which for C++ will be a vector of vectors, and for Python will be a list of lists. And our goal is to get a 1 down in the bottom corner here, which will basically represent whether it's possible or not. And everything will be initialized to 0, or you could use booleans if you want, true and false. And we'll initialize just the first element in the top left-hand corner of our 2D data structure to be 1. And basically what this is going to represent is that whenever we have 1 in this column, we're trying to match, or in this row, we're trying to match a letter in our string A to the current character in our string B. And if at any point we can do that, we're going to sort of skip down here and move along to try and match a character at the second position, or third, fourth, and fifth, depending on our example. And so whenever we skip down a row, that means we've matched a character. And if we are just moving horizontally, that means that we had a lowercase letter here and we were able to drop it. So we're basically going to set everything in our right-hand column equal to the left-hand column when we don't have an uppercase letter, because if it's lowercase, we know we can just basically continue to move on. But if it's uppercase, then we are not going to be able to set everything equal to what is on the left. And so we have to see if when converted to an uppercase, or if it is an uppercase, we can make this match the current character that we're going to. So that might not made a lot of sense as I said it, but we're going to walk through this and show sort of the path to a valid solution if it's possible. So At this point here, we just have at index 0, 0, we're trying to match capital A. And so here we have a lowercase a, and so because it's lowercase, we can set the next column at the same row, index j, so just basically j and I plus 1 equal to 1. And because we also are able to match this lowercase a to the capital A here, we can set j plus 1 and I plus 1, so this square here also equal to 1. So this is due to the fact that this is lowercase moving horizontally, and then moving plus 1 in our row and column is due to the fact that we can match this a with this a when we capitalize it. So then we move on to our next column here. So because this is lowercase, once again, we're going to be able to set horizontally this square here and this square here equal to 1. But due to the fact that this b, when capitalized, does not match the a, we can't do the j plus 1, I plus 1. So this will be 0 because we're not able to match this b to the a. So basically, the only thing we're able to do with this column, because there's no b in our final solution, is to remove it. Then we move to our third column here. Once again, this is lowercase, so we'll be able to set these two squares both to 1. And because we're able to match this a with our second a, we're going to be able to set this square here equal to 1. So j plus 1, I plus 1 at this box produces this box down here equaling 1. So we're going to do the same thing now with this character. Once again, this will be 1, this will be 1, and we have two cases here. We're only actually doing the horizontal setting of the next column to be equal to the left column when j is less than the number of rows. So at this point, it's greater than, so we don't do that, but this a does match this a, so we're going to be able to set this to 1, 1, 1 as well. And then for our final column, at this point, our a is now capital, so we're not going to be doing the horizontal setting. So this will end up being 0 because we can't horizontally match, which basically just means that this has to be in our final solution because it's capital. And at this point, we are still going to be able to match this a to this a, and then this will get us to 1. And note that even though we have a 1 here, it doesn't contribute to us setting this final box down here to be 1 because this is capital. So this may not mean a lot, but basically at the end of the day, there were 3 different ways that we could get our final string b. The first one is follows. So you can see here we matched the first a and then dropped all of the characters. So this is the step down here is matching this a, so it's sort of the column corresponds to the next one. Then these 3 lowercase letters were dropped here. There's no drop step down, and then we used the last capital A here. And there's 2 other paths. We basically drop the first 2, keep the second a or the third character, drop the fourth character or the third a, and then include the last one. And then the third path is to include this a and to include the last capital A as well. So this is not entirely clear, but we're going to take a look at one more example, which hopefully clarifies what's going on here. And that's where there's only one valid path to construct our or translate our string A into string B. So here we've done away with the sort of diagram and we're just focusing on our 2 strings. So we have A, B, and A. And note that the 3 inner characters are all lowercase. And so that means the first and last character are both capitals, which means that these need to be included in our final string because we can't remove them. And which means there's only going to be one path, and that's removing the middle 3 and keeping the first and last characters. So we have our same initialization here, 1 in the index 0, 0. And so we're just going to walk through it once again. So taking a look at our capital A here, because it's not lowercase, we're not going to be able to set this square equal to the square to the left. So this will be 0. But because A and A do match here, we're going to be able to set j plus 1 and I plus 1 from our current square, which will then come down here and set this to 1. And then this will be 0 because this is 0 here. So then we have this, we move to our next column here. So we're looking at this B. The B does not match either of the a's here, but it is lowercase. So we won't be able to do a j plus 1, I plus 1 setting, but we will be able to do an I plus 1. So basically copying this one from the box it's in to the box to the right. And we're basically going to be able to do this 2 more times until we get to the last column. So actually, because this A did match our second A here, we were able to do a j plus 1, I plus 1. But then when we get to this column, we're no longer going to be able to do a j plus 1, I plus 1. But because it is lowercase, we are able to copy both of these ones over and the 0 over as well. And in our last column here, we have a capital A, which means no copying from one column to another. But we are able to match this A with the last A. So we will copy this one basically down into this square here. And so note that there is only one path. So due to the fact that the A in the last column was capital, this one, once again, did not contribute to this bottom square. It was just this square here, which leaves us with this path. Using the first A, which is represented by this step down, the last A, which is represented by this step down, and then the 3, sort of shifts to the right, equal dropping these 3 middle characters. So it's actually reusing sort of the relationships that we identified in our recursion, but just not doing it recursively and setting up a DP 2-dimensional vector or list, and then using this sort of relationship that's dimensioned by the length of both of these strings to get to whether or not it's possible to convert A to B. So all that being said, let's take a look at our code. So here is our C++ solution. You can see, similar to the previous video on dynamic programming, we have our function that just takes 2 strings, A and B. At the top here, we're just declaring 2 local integers that are going to conveniently store the sizes of our strings. And then we're declaring our 2-dimensional vector dp here. Note that we are dimensioning it to be +1 on the size n and m to get that extra row and column that we're trying to reach. And then we're initializing index 00 to be 1. Then we have nested for loops here for I less than n and for j less than or equal to m. We're basically checking, were we able to get to this point in time matching? If not, skip to the next iteration. If so, we do our 2 checks. If j is less than m and either the character already matches the current uppercase character in B, or it's a lowercase version, and when we make it uppercase, it matches. Then we do our +1 on I, +1 on j, and set that equal to 1. And then our second condition is checking as long as it's not an uppercase letter, we can just ignore it. So that's the deletion, and then we just set I +1 and keep the current j equal to 1. So that's the horizontal shift. And so when we continue to do this, we're basically going to fill up our 2-dimensional vector or list as was shown in the visual example, and that will do it. And so at the end, we just need to check, is the value in the nm index or element, is it set to 1? And if it is, then we want to output yes. If it isn't, we want to output no. So pretty straightforward. A lot of the code is a lot cleaner than the alternative recursive solution, and so yeah, I'm guessing that in future problems, whenever you have a recursive function that partially solves it, you might be able to convert that recursive relationship that you found into a sort of dynamic programming state-based solution. And so we'll also take a look at the Python solution, which is very, very similar. At the top, just setting n and m to be the length of A and B, setting up our 2-dimensional list of lists, initializing the index 00 to be 1. Then we have our 2 nested for loops, the same if our dp element at this point is not equal to 1, then continue on, and then the 2 same conditionals if j less than m, and our current character as it is, or when made upper, is equal to our current character in B, +1 on I, +1 on j, set equal to 1. And as long as it's not an uppercase letter, we can remove it. So I +1, j equal to I. And then we have our same return yes if the element at nm in dp is set to 1. Otherwise, return no. So the last thing to talk about is the time complexity of this problem, which is going to be quadratic. So I have here big O of n squared. Technically, it's actually big O of n times m more accurately, as we're doing a nested for loop over those two ranges.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.